Let's investigate the concept of equilibrium, which is also known as statics. Remember that we are already familiar with the concept of translational equilibrium, and the way that mathematically we could satisfy this particular state is by using Newton's first law, which is that the sum of the forces is equal to ma. So remember that if we had an object which was subjected to, say, a force F1 of a known magnitude, let's say directed down on our object, F1 being an external force, for this system to be at equilibrium, we needed to have another force, F2, of the exact same magnitude but opposite direction, such that if we sum all the external forces acting on this particular object S of mass m, then F1, which is directed down, is equal to minus F2, since both forces have the same magnitude and opposite direction. If we move F2 on the other side of the equation, it becomes plus F2, so F1 plus F2 is equal to 0. Since F1 and F2 are the only two forces acting on our system, then this represents the sum of all the forces. And indeed, in this case, our system is not able to accelerate in the y direction if we choose this to be our y and this to be our x. So whenever we have static equilibrium, and specifically translational equilibrium, we know that the sum of all the forces acting on the subject must be equal to 0. Now think of it as degrees of freedom. An object can be translating in all direction towards the x direction, can be accelerated towards the y, it can be accelerated towards the z. So in order for our system, or to prevent our system from being accelerated in any direction, then we need to make sure that the sum of all the forces in the z must be equal to 0, all the forces acting in the x must be equal to 0, and all the forces acting in the y must be equal to 0, such that the degrees of freedom have been reduced from 3 to 0. And in this case, we are all familiar to this, which can be rewritten as sum of the forces in the x, sum of all the forces in the y, and if you're working in 3D, sum of all the forces in the z direction must be equal to 0. So this was what we've been using for translational equilibrium. Now remember, when we were using and applying Newton's first law, and we had a system with a bunch of forces acting on it, what we could do to simplify our free body diagram is we were able to move the forces any way we wanted. Since forces are represented by vector, which are defined by both their magnitudes and directions, if we don't change any of those two, we can just move that vector around. So we could represent this system, well, let's imagine it's the same system, same shape, by considering the center of mass of our system, and by moving each force and applying them and redrawing them starting from our center of mass. And this will allow us to be able to represent our free body diagram and all the angles needed, alpha, beta, whatever, and being able to write down our equation easily. That was okay, and I was perfectly fine in translational. When we are going to investigate our new topic, which is this case rotational equilibrium, we will not be able to do this. We will not be able to move the stuff around because the position at which each force will be applied to is going to be important as we calculate the torque created by those forces about a particular point. So what is the difference between Translational equilibrium versus rotational. Well, let's go back to the exact same example. A system S of mass m being subjected by two forces F1 and F2, which have the exact same magnitude but opposite direction. But this time I'm going to apply F1 here and F2 over there. In this case, we are still under translational equilibrium because if we do the sum of the forces in the y direction, we will end up as F1 minus F2 or vice versa. F2 minus F1 is equal to 0. Therefore, the system is not being accelerated in a linear dimension, in this case, the y. Therefore, this system is still at translational equilibrium. But if you think of this system in terms of rotation, you will see obviously that this system will tend to rotate, in this case, in the counterclockwise direction, even though the sum of the forces is equal to 0. So it is possible to have a translational equilibrium satisfied, but not a rotational equilibrium, even though the forces are the same. It all depends on where and how those forces are acting on our system. So you will have a particular angular acceleration every time you have a non-zero torque. And this can be created by forces even though the sum of the forces is equal to 0. So sum of the forces equal to 0 does not necessarily mean that sum of the torque is equal to 0. We need to treat them separately. So in order to express mathematically rotational equilibrium, we are going to use sum of the torque, the same way as we have expressed translational equilibrium by using Newton's first law, which was the sum of the forces. So whenever you're interested in figuring out whether a system is in rotational equilibrium, all you have to do is use sum of the torque is equal to 0. If you're being told that the system is at equilibrium, but you are not being specified whether it's rotational or translational or both, if it's not specified, you can always assume that both rotational and translational are being satisfied, which means that you are able to use sum of the forces equal to 0 and sum of the torques are equal to 0 in order to solve for this particular problem. So let's see how sum of the forces, sum of the torques work. First of all, you will need to figure out how many terms are going to show up in the left-hand side of your equation. Now, every time you have a torque, the source must be a force, because by definition, torque is R cross F. So technically, every time you will see, let's say, n forces acting on your system, guarantee you have at most n torques. So let's say you have F1, F2, F3 forces acting on your system, then you know that there's going to be a force due to F1, a torque due to the force F1, plus a torque due to the force F2, plus a torque due to the force F3 acting on your system. So you're always going to know the number of terms that will show up in your equation. So this is the most amount of terms that will show up, that could be present. Now some of those torques could be 0, and there are several ways that a torque can be equal to 0. First, R, this little r, could be equal to 0, which means that you are going to calculate the torque at a particular point where the force is applying to, and therefore the r is equal to 0. For example, if you have an object, let's use the same object. Point A is here, point B is here, point C is here, point D is here. If you are going to calculate the sum of the torque at point B, obviously the torque created by F1 is going to be equal to 0 because R is equal to 0. That's the first possibility, that one of those terms here could be equal to 0. The second possibility is if R is parallel to F. In this case, based on the property of the cross product, if R is parallel to F, the cross product will be equal to 0, and therefore the torque will be equal to 0. For instance, if you calculate the torque at point C, R is position vector CB, and therefore R cross F is 0 because R is parallel to F1. So in this particular case, the torque will be equal to 0. So you can drop terms by identifying cases where either the R vector is equal to 0 or R is parallel to F. Let's look at a simple example. Let's imagine that we have a square, point A, B, C, D. Let's imagine there is one force F2, another one F1, and let's say another one here called F3, such that this angle is alpha. If you are being told that this is a static problem, which means that the system is at equilibrium, then you know for sure you can use sum of the forces equal to 0 and sum of the torque is equal to 0. Let's imagine we have satisfied the first equation, which was the translational equilibrium, and let's focus on the rotational equilibrium being satisfied by this equation. I want to use this to, let's say, figure out and satisfy the fact that my system is under equilibrium. I want to calculate the sum of the torques, therefore I know that I have three forces, F1, F2, F3. Therefore I'm going to have three terms, torque due to F1 plus the torque due to F2 plus the torque due to F3. And this must be equal to 0. Now by definition, remember that every time you calculate the torque, you will need F and you will need R. F are given to us, so it means that for every torque that we are going to calculate, we will need the R. So let's call the first one R1 cross F1. For the second term, we will need R2 cross F2. And for the last term, we will need R3 cross F3. Now, let's imagine that we are being given those forces. The first thing that we need to do is identify those R vectors. By definition, remember that this R always starts where you have decided where to calculate the sum of the torque. And if you're dealing with a system at equilibrium, you can pick any point you want. Remember, if the system is accelerating with non-zero alpha angular acceleration, you have to use the center of rotation point. If this axis of rotation at a particular point is fixed. If the axis of rotation is not fixed, but instantaneous, which means at every instant that particular axis changes its position, then you have to use the sum of torque at the center of mass of the object. For the case where you have equilibrium, you are free to pick any point you want. So, since you can pick any point you want, you can pick point A, you can pick point B, point C, point D, point E, or point F, which is not even on this page, like 3 miles away. You can pick any point you want. You are and should get the same answer at the end. So the next question is, which point are you going to pick? Now you know that the torque is going to be equal to 0 if R is equal to 0 or if R is parallel to F. So usually when you calculate the sum of the torque, you want to pick a point where either the most amount of forces are acting on that point, or a point where the most amount of forces are aligned with the R vector. So let's imagine in this case, I am told, for whatever reason, to pick a particular point. Let's imagine that I'm told to calculate the sum of torque at C. Again, it is a fictitious situation. If you are dealing with a static equilibrium, you're free to pick any point. I just want to pick point C because otherwise it's going to be too easy. So at C, therefore, I need to calculate and figure out R1 cross F1, R2 cross F2, R3 cross F3 about a center or an axis of rotation which is centered at C, perpendicular to that page. Which means that R1 will be the position vector starting from C, and this position vector ends where the force is applied. This is how you figure out the vector R. So for the force F1, I know that all my vector R1, R2, and R3 are all going to start at point C. For R1, it will end where F1 is applied, and F1 is applied at point B. This is the reason why we cannot just move the forces around as we did for translational equilibrium, because if we can move the forces around, we're going to change the R vector, which will change the whole system. So F1 is applied at B, therefore R1 must be position vector CB. Now let's imagine we know Los distances. Let's call it A meters, A meter, A meter, it's a square. In this particular case, if R1 is CB, this is the same as AJ. F1 is directed down. It has only one component, which is the J direction. R1 and F1 are parallel to each other. They're acting on the same line of action. Therefore, the torque due to F1 is obviously 0. Because again, R1, where's my toolbar? R1 is from here, from C to B. R1 is parallel to F1, therefore the torque is 0. Let's do the same thing for F2. We need to identify R2. R2 starts at point C, again, and ends where F2 is being applied, which is also point B. Therefore, R2 is going to be AJ, again, CB, position vector CB. F2 is a line in the I direction. I is different from J. In this case, we're going to have a torque, which in this case will be counterclockwise, therefore positive. The torque due to F2 will be a F2K. Now, how do I know that it's K? I know that it's K because I know that if position vector and F are in a plane, then the torque is perpendicular to that plane. But how do I know whether it's coming out of the plane or going into the plane? Remember that the convention is to use I, J, K, which are aligned within our x-axis, y and z-axis. There is a nice mnemonic trick that you can use. I, J, K, I, J, K, I, J, K. Whenever you go towards the right, it's positive. Therefore, I cross J is positive K. J cross K is positive I. K cross I is positive J, and vice versa. I mean, keep going. So every time you go towards the right, the cross product is positive. Whenever you go towards the left in this sequence, for example, K cross J will give you minus I, and J cross I will give you minus K. I cross K will give you minus J. So that's easy to remember. Right positive, left negative. So in this case, I'm doing R2 cross F2. I have J cross minus I. So let's forget about this one. We'll put it after. J cross I. I need to go towards the left. Oh yeah, when you use that little trick, you cannot skip. You have to use the adjacent guy. So J cross I, obviously we have to go towards the left. This will give us K. Since we're going towards the left, it's minus K times this minus 1 plus K. Therefore, positive AF2. Okay? Okay, Last one, let's calculate the torque due to F3. So R2 was exactly the same as R1. Now for R2 needs to start at C, because again, it's the point at which we decided to calculate the torque. And this position vector will end where F3 is applied to, which is point A. So here we could either project F perpendicular to R or project R perpendicular to F, or we can just express R3 in vector notation. R3 will be minus A plus A in vector component. F3, which is applied at point A, is going to be F3 cosine alpha. Did I use alpha? Yep. And F3 sine alpha J. Therefore, the cross product, or the torque created by F3 at point C, will be minus A0, F3 cosine alpha, F3 sine alpha, 0. This will give me a K vector. I will consider this 2 by 2 matrix, which is minus A F3 sine alpha. This times this, minus this times this, minus A F3 sine alpha. Therefore, minus A F3, what? Cosine, sorry. Putch. F3 sine alpha plus cosine alpha. And this is K. Therefore, this torque is clockwise. Same as F2. This is odd. F3 is clockwise. Book, book. Okay, yep. So that's an example where matrix is nice. Because the torque created by F2 obviously is counterclockwise. Therefore, we expect this to be positive, no problem. Now, if you look at this and you try to figure out in which direction is the torque created by F3, most likely it's going like this, but sometimes one of the components might be giving you another one. So some of the components in 2D, there's going to be two components. One might be positive, the other one might be negative. If you're not sure in the direction, just set up the matrix. So that's it. So in general, let's say you have a system like this, where point A is here. Let's say you have a force here, you have another force here, you have another force here, which points to A. You have another force there. And let's say this system, you have one force, one force, one force acting at B, another force here, another force here. For situation 1, situation 2, at situation 1, how are we going to choose the point at which we want to calculate the sum of the torque? Well, there is no point where there is more than one force is acting on it. However, there is one point where several forces converge. This one, this one. This one crosses here, and this one crosses there, so we miss it. But those two converge at this point. Therefore, we know that if we calculate the torque about A, the torque created by this one and the torque created by this force will give us 0, because R2 is here and R1 is here. So you just got rid of two terms. So from 4, you only end up with two non-negative torque. At situation 2, obviously there is a point where there is a lot of forces acting on it. And if you're lucky enough to be able to look for those two, then definitely you want to calculate the sum of the torque at B, so that the torque created by this force, and this force will give you 0 terms because the R is 0, which will simplify the algebra overall. So remember, the two ways that the torque can be 0 and a way to minimize the number of terms showing up in your rotational equilibrium is to figure out either a point where there is a lot of forces acting on it, so that R is 0, or a point where the direction of all the forces converges, which will give you an R parallel to F, which will produce a zero torque. So in summary, remember that there are two types of equilibrium. Translational, which is verified by the sum of the forces, and rotational, which is verified or expressed mathematically with the sum of the torque. You can have one without the other, or vice versa. Remember that when you're doing the sum of the torque, you are not allowed to move the forces around because otherwise you will move and change the R values. And R is crucial in determining torque. You will see another type of beast later on, which are called couple. And actually, this is an example of one where, in fact, the point at which you calculate this value doesn't matter. But those are special types of torque. In general, the position at which you calculate the torque is important every time you have non-static situation. So in case of static equilibrium, where rotational and translational are present, you can pick any point you want. If the system is not in static equilibrium, remember that you have two options. If the axis of rotation is fixed in time and in space, you have to calculate the sum of the torques about this particular point. If your axis of rotation changes or is a function of time, or changes its position as a function of time, then you want to calculate the sum of the torque about the center of mass of the object, which you will need to calculate and identify before you can calculate the sum of the torques. And another key element of calculating the torque is to remember that you always need to make a choice at which you're going to calculate the sum of the torques. Again, if you have static equilibrium, you can pick any point you want, but you have to be very clear about which point you choose, because the choice of your point at which you calculate the torque will have an effect on the value of your position vectors, which always start where you decided to calculate the sum of the torques and always end when the forces are applied to. And remember that little trick, if you don't want to use matrices and those forces are perpendicular to each other, so you don't have to worry about the angles, you can use IJK, IJK, IJK is positive towards the right, negative towards the left.